Today is December 4th, 8:52 Pacific time. And let's get more people in.
Good morning, Professor.
Morning. Okay, so let's start sharing the screen. Today is the last day. Oh, how time flew by, right? Last day of lecture meeting, right? We're not gonna have a lab today. I want to take advantage of this day to cover as much material as I can since we fell behind. Usually doesn't happen to me because I am able to cover what I want. But this time, for some reason that I still don't know, we fell behind. So let's start sharing the screen here. Let's take a look at the syllabus. Here you go. Wednesday, 4th of December, 2024. Go. We're gonna start fluids. We finished simple harmonic motion. There will be only 4 sections in the simple harmonic motion chapter. I can finish the fluids chapter rather quickly because it's rather simple, no advanced. It's very, all we need is algebra, okay, to cover fluids. And let's take a look at the section on fluids, right? So here we go. Those are the sections we are gonna cover. Let's take a look at the book. So you can cross-check with the book as well. Wiley Plus. Let's go there. Login. Okay, simple harmonic motion is here. Da, 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 da. Okay, I don't usually have time to cover those two, so there will be no homework for them, and there will be homework for fluids. And let's see if we can cover those other 2 chapters here, right? If we're not able to cover those 2 chapters, you won't need to worry about them. Okay. So more 2 students joining us, and we want to go to Y course. Computational dynamics, we want to go to chapter 11 right in here. Those are the topics we are going to cover. 1, 2, 3, let's see. 1, 2, 3, and 6. 1, 2, 3, and then we skip to 6. Okay, we are not gonna do the rest, the other ones. And the ones that I judge more important. So the first thing that we gotta know, let's talk about the idea of mass density. Mass density, most likely you have already seen this concept of mass density. And mass density or mass density, right? Density or mass density. He specified mass density because there are other types of densities as well, okay? And it's a very simple idea. Is what mass density is the amount of matter per unit of volume. That's what it is. If you, for instance, for instance, get 1 cubic centimeter, right? cc for cubic centimeter of water, and 1 cubic centimeter of gold, right? Gold, the mass of gold will be larger because gold is denser than water, okay? So the formula for density, the definition of density is the following. The definition of density is the following. Here you go. Mass over volume. And the unit of density is the unit of mass divided by the unit of volume. If we are talking about the SI units, it's going to be kilogram per cubic meter, but there are other types of densities as well. Okay, can be grams per cubic centimeter. Okay, the main SI unit for density, the main SI unit for density is the kilogram per cubic meter. However, we still can have other types of density, like the gram per cubic centimeter, cc, right? And we can invent many other types of density. Let's say gram per cubic decimeter, right? Cubic decimeter, and so on, okay? Like, well, there is one type of density that there are tables, let's say, there are tables of density with several different materials. Substances, that was substances instead of materials, substances. The most important one is the easiest one, is also the easiest one to memorize. The density of water. The density of water. Okay? And how does the density of the water go? It goes very easy to memorize that, but remember, it's going to be not in the SI unit, it's going to be in the other unit, gram per cubic centimeter. 1 gram per cubic centimeter. Can you remember that? 1 cc of water, 1 cubic centimeter of water has a mass of 1 gram. So when I want to know the volume of the, let me give you an example, okay? Many other liquids out there has a density that is very close to the water. And by liquids, I mean, orange juice, for instance, I never measured Coca-Cola, but Coca-Cola may have, I presume that Coca-Cola has a density similar to water as well. Let's take a look. What's the density of Coca-Cola? Just for curiosity's sake, right? What's the density of Coca-Cola? What's your favorite drink, right? Density of Coca-Cola. Yeah, let's see. Must be very close to that, the water, I suspect. Oh yeah, see, that's very close to that of water. Milliliter is the same as a cubic centimeter, okay? So 1.042 grams per milliliter, or 1.042 grams per cubic centimeter. What about beer? I don't drink beer. I don't drink Coke. Okay. Let's see. The density of beer, also known as specific gravity, just another name for density, can be measured using a hydrometer. But what's the value? Okay. 5% ABV has an original gravity of around 1.04, very close to that of water. Okay? Very close to that of water, as you can see. So when I'm drinking my juice, I like to drink juice, and I want to know how much, and I keep track of how much juice I drink during the day. I want to know how much, how many milliliters of juice I'm drinking. So what do I do? Instead of measuring the volume in a cup, what do? I have a scale, a very nice scale here that I keep in my kitchen. And I put the empty cup there. I tear the scale. I zero the scale because otherwise I'm going to be measuring the mass of the cup, the empty cup as well. So I tear the scale. I zero the scale, right? When I tear the scale, it becomes 0 grams, and then I pour my juice into my cup. So let's say I got 300 grams in the scale. Since the juice has a density similar to that of the water, I know that 300 grams of juice correspond to 300 milliliters or 300 cubic centimeter of juice. Okay. Now, if you want to change this density to the other units, right? But let me finish this one. Many other liquids out there have a density very close. That's very close to that of the water. The orange juice, for instance, Coca-Cola, Coke, right? Beer, etc. Now let's see how this density here, this unit of density, can be written down in terms of the unit in the main SI unit, right? So here we go. 1 gram, you already know that 1 gram is what? 0.001 kilogram, right? Or if I write down in scientific format, it's 10 to minus 3. That's what 1 gram, don't mix that up. This G is the acceleration of gravity, right? Is the G that is the unit. So here you go. So what I have to do is substitute the gram by 10 to minus 3 kilograms. 1 kilogram is 1,000 grams. And then you do the same for the centimeter, right? But you gotta do only for the centimeter. Not, okay, he doesn't like it. Let me try. Like that, here you go, better now. The little tricks of the software, right? And now what do I do here? I replace the centimeter with its equivalent of meter. Very straightforward trick, right? 1 centimeter is 10 to minus 2 meters, right? Or 1 meter is 100 centimeters. And now we can convert this unit into kilogram per cubic meter. But first, we gotta get the cube of this one, right? There's a little trick here, right? Make sure the 10 to minus 2 meter is going to be raised to the cube, okay? When we raise it to the cube, we got 10 to minus 6 here. We got cubic meter. Now, here you go, like that. And, okay, I'm going to 10 to minus 3 minus, you go -6, right? I'm just passing the 10 to -6 upstairs. And then what are we going to get? +6. Minus is minus plus. Here you go, +6. And then you go 6 minus 3 is +3. So the density of water is, 1 gram per cubic centimeter or 1,000 kilograms per cubic meter. Water is a rather heavy substance, right? 1 cubic meter of water has a mass similar to the mass of your car. Okay, so I'm gonna put it here. That's how we convert from one unit to another one. The same technique can be used for many other types of conversions, many other types of different conversions. Remember that? This one is easy, right? And if you forget what is the density of water in kilogram per cubic meter, just go through this algebraic process to find its value, okay? Okay, that's the concept of, let's take a look at the table of densities, right? Table of densities. Okay. Let's see, hydrogen gas, the hydrogen gas. Very small, 0.00089 grams per cubic centimeter. Okay. Carbon dioxide gas as well, 0.0019. Let's see, do we have air here? I don't see air here, unfortunately. But it's important to take a look at least take a look at the density of air, right? You don't have to memorize, but at least it's a good idea to be exposed to gases. Let's see, air. This one is approximately 1 times 10 to -3, approximately the density of air. And that was going to be the unit gram per cubic centimeter. Okay, if you're going to memorize it, just memorize it at 1 times 10 to -3 grams per cubic centimeter. It's not difficult to memorize the air. And liquids, water, right? See the water here, 1. Salt water is slightly higher than that. Salt, like I said, this is slightly higher than that, not much higher than that. Antifreeze, 1.11, 10%, 11% higher than water. Salt water, oh, here you go, salt water. But it's saturated salt water, it's not seawater, okay? Seawater is not saturated. So if you go to the highest possible density, if you dissolve the highest possible concentration of salt in water, you end up with a density that's 20% larger than that of the pure water. Okay. Look at the density of liquid mercury. Liquid mercury is very dense, 13.6, extremely dense. 1 gram of 1 cubic meter of mercury has a mass of 13 grams, 13.6 grams. Platinum, solids here. Gold, uranium, tungsten, lead is very dense. Silver, copper, nickel, so on. Balsa wood. Okay, balsa wood is very light, 0.1. Cork, I saw cork. Did I saw cork here? No, I didn't see cork here. Bamboo, oak, paraffin wax, ice. Ice, it depends on the temperature. Okay, the density of ice depends on the temperature. But the ice that they're talking about here must be at 0 degrees. They didn't say the temperature. Okay? is ice is lighter than liquid water. Solid water is lighter than liquid water. See that? The density is lower, 10% lower. Plastic, solid salt, glass, granite, magnetite, magnesium, aluminum, and so on. Okay, let me copy and paste this one. This snipping tool. So density is a very important concept in physics, and you know, and you can take advantage of this idea. Table of density, table of densities, of density. Let's see if I can get it smaller to fit in that page. Yeah, it's not fitting, is it? Okay, let me keep it separate page. You know what? Let me see if I can put it. Here we go, table of density. Okay. Table of densities. Densities. Okay. Don't forget, air is 10 to 1 minus 10 to minus 1 times 10 to minus 3, right? 1.2 if you want to go through the process of, and notice that nitrogen and oxygen, they have densities that are very close to that of air, right? Air is a mixture of both. A mixture of both. Okay, so we're done with this idea of density, mass density, here you go. And there is this other important idea, that's that of pressure. Let me get this thing here, copy. Right, now I can boldface it. Boldface means that we already covered it. What about the idea of pressure? Okay. The idea or concept of pressure, this is another important concept. Let me let me show you an illustration. Here you go, fluids, idea of pressure. Suppose that you go ahead and get a block, 1 square meter of block at the top here, a parallel pipe, right? The area here at the top 1 square meter, the area here at this side is half square meter, let's say. It's not in scale, okay? Obviously, it's not in scale. This block has this mass of 10 kilograms. And this block is also exerting a force on this surface, okay? So let's go ahead, consider consider a 10 kilogram parallelepiped on the top of a surface. Okay, here's the illustration. The illustration looks just like that. This block has a square cross-section. The longer length has an area of the smaller, the greater length, the largest, right? Length has an area of 1 square meter. And the smaller one, half a square meter. Like I said, this illustration is not in scale, it's just for illustration purposes. On the top of that, the block exerts a force of approximately 100 newtons on the surface it rests. Okay? Make sense? I'm gonna need this. The pressure, here you go. The pressure that the block exerts on the surface is given by, I'm gonna need that. The definition, the very definition of pressure is going to be the force divided by the area. Can you remember that? Okay. The force is exerted. In this specific case, the force we already know is 100 newtons. And I also told you that the area, the contact area, here you go. Let's write it down, contact area, right? It's very important. Contact area, force. Now at this point in time, you already know that the contact area, 1 square meter, right? And the pressure becomes 100 newtons per square meter. 100 newtons per square meter, according to this definition of pressure. Which, by the way, is a unit that shows up so frequently. The pressure due to the solid only, okay? This unit of pressure shows up so frequently that we give it a name. We call it the Pascal SI unit and abbreviate by PA, okay? 100 Pascal. 10 kilograms, 100 newtons, right? 1 square meter, and so on. However, note C that the pressure depends not only of the mass of the solid, of this solid, right? Let's put it, of this solid, but also on its area of contact, okay? So if we reorient the solid, instead of laying down in its side, we orient it to lay down on its foot, right? On its foot. We're going to end up having a different pressure. The mass doesn't change, but the area of contact does. Oops. The area of contact change, right? Do you get the idea? Now let's find the pressure for this situation here. Okay, now look at the above figure. Now look at the above figure. It is the same solid with the same mass, but oriented differently. With another thing, oriented different, and consequently with a different point of contact, different area of contact instead of point. Let's put area of contact. In this specific case, now the pressure becomes 100 divided by half, right? Half square meter, which ends up being what? 200 Pascal. Okay. This makes sense, right? This makes sense, right? After all, it is far more painful to stand on the tip of your toes, than, let's say, to lay down on the side or back on your side or back, right? Your side, back, side, front, or back. Okay? So pressure is a measure. So pressure is a measure of the concentration of a force. The smaller the area, for a given force, okay? For a given force, the smaller the area, the more the concentration of the forces, the greater the force concentration. That's what pressure is all about, the measure of the concentration. We can even go further and say another way of thinking about it, okay? Another way of thinking about that is saying that pressure is a force density, right? But it's a density, density in this case, with respect to an area instead of a volume. Okay? This is the idea. This is the idea of pressure illustrated by the case of a solid, right? But pressure is something that can be extended to fluids. And by fluids, what do I mean? Liquids and gases, okay? But pressure is a concept, not something, but it's a concept that can be extended to fluids, liquids, and gases. Okay, and I'm going to illustrate that for you right in here. Pressure due to a fluid. Consider the fact that we are all submerged in an ocean of air, in an ocean of gases, oxygen and nitrogen. Most of it is oxygen and nitrogen, a little bit of carbon dioxide as well, okay? And all these gases, they exert a weight over our heads, okay? Here is an illustration of the Earth and the atmosphere of the Earth, which extends up to a certain height. Okay, some people would say extends all the way up to 100 kilometers. That's a good rule of thumb. 100 kilometers high. That's what the atmosphere extends to. So much that the International Astronautical Federation consider anything above 100 kilometers the beginning of space, okay? If you fly above 100 kilometers, you can be considered an astronaut. Anybody who flies above 100 kilometers, you don't even have to orbit the Earth. Just get a very powerful airplane or rocket, jump into the rocket, fly above 100 kilometers, and yeah, you became an astronaut. You became an astronaut, okay? And here you go. Here we are sitting on the surface of the Earth. And by the way, it's very difficult to fly above 100 kilometers, okay? It's so difficult that very few people has achieved to do that, has managed to achieve to do that. Only now that we're starting to commercialize space flight, that more and more people are having the opportunity to fly in space. But don't forget, flying above 100 kilometers is far easier than orbit the Earth. Okay, orbiting the Earth is a far more larger step. It's far difficult to put an object in orbit than to fly above 100 kilometers. To fly above 100 kilometers is already difficult. No airliner can do that. Not even the supersonic jets. Okay? Supersonic jets that we have out there. But then you need, in order to fly above 100 kilometers, you're going to need an airplane that has a rocket fuel, just like a spaceship 2, spaceship 1 and spaceship 2, right? Well, okay, so going back to the concept of pressure, right? So you have this huge column of air on the top of our heads, okay? And this huge column of air is exerting a pressure on our body. And this pressure is a number that is rather easy to memorize, okay? But that's how you should think about pressure due to gases and liquids. Okay, so let's write that down. For instance, we are all submerged in an ocean of air, a mixture of oxygen and nitrogen, and traces of carbon dioxide and other gases. Traces of carbon dioxide and other gases, right? Let's see which other gases we have in the atmosphere. Most of it is oxygen, and we do have the density of oxygen and the nitrogen here, right? Nitrogen, oxygen, where is oxygen? Oxygen. And then here you go, the density of air. But composition of air, right? Composition of air. Here you go. Artificial intelligence. Now we have this artificial intelligence helping us out, right? AI overview. Air is made up of a mixture of gases. Nitrogen, 78%. Oxygen, 21%. Okay, it's okay to say that the air is made up of just oxygen and nitrogen, because most of it, we're talking about 99% of the air is made of oxygen plus nitrogen. Then we have small potatoes contribution from argon, carbon dioxide, water vapor, and so on, right? Argon is less than 1%. Carbon dioxide is less than a tenth of a percent, and so on. Industrial pollutants, right? Now is the industrial revolution. Now we are changing the composition of air, but it's still very small compared to nitrogen and oxygen. Sulfur compounds, okay, so on. 932, okay? And, okay, so this idea of pressure illustrated by the case of a solid. This is the idea of pressure illustrated, but pressure is a concept that can be extended to fluids as well. For instance, we are all submerged in an ocean of air, a mixture of oxygen and nitrogen and traces of other gases. Let's put out other gases. Okay. So try to visualize that we are all subjected to a column of these gases that extend to approximately, 100 kilometers high. It's a 100 kilometers deep ocean of gas, oxygen and nitrogen. All these gases, although they are very light, they do exert a force on us. Okay? Let us calculate how much is that. Let's see. Now let's leave this way. Okay, let's leave this way. However, there's an important difference. There's an important difference. How gases and liquid exert pressure on an object compared to the pressure exerted by solids. Okay, there's a very important difference. The pressure is not just downwards. The pressure by these gases, by these fluids, right? By a fluid, it's not just downwards, but also sideways. And I'm going to illustrate that for you. Can you remember that? So with this funny pressure, here you go. Here's my block again, right? Here you go. Here's the pressure that air exerts over my block, over my block here. Not only we have this component downwards, but we also have this component sideways. That's always perpendicular to the surface. Okay? Normal, not perpendicular, but normal to the surface. The pressure, let's write it down. The pressure exerted by fluids on an object will always be normal to the surface. Okay? And now we can extend this idea. Here you go. Do I have it here? Let's see. I don't think I need this illustration, right? Yeah, we don't need this illustration here. Let me get rid of it. And here you go. Now we're gonna play with a recipient of water. Okay, here you go. Here's my empty recipient, my jar. All right, I'm gonna put some liquid in there, water. Not only we have the weight of the atmosphere, the pressure of the atmosphere exerting on the surface of the water, which is, here you go, approximately 100,000 newtons per square meter, okay? That's the approximately 100 kilopascal. Can you remember that? But if we dive deep below the water, there will be a pressure exerted by this column of water, which is going to be added by the pressure of the column of air above it. Can you picture that? Okay. And we can calculate that. We can calculate that. You go. It's possible to calculate this pressure. So very simple. So a very simple procedure. Consider that you have the cylinder of water at this depth. Here's the H, depth H, right? Cross section A. I'm going to put my object here. Let's see, my object here underwater. Here you go. We have the pressure of the air again and the pressure of the water, and they do sum up. But like I said before, we also have a pressure sideways as well. As we go deeper and deeper, this pressure increases because we have more and more water above us. Okay? But at the same depth, I want to be more here. Let me get this guy here. Go. Yeah, better now, right? Here you go. Okay. Not only we have in the vertical direction, but we have in the sideways. This pressure here on the side cancel out this other pressure here on the side. Okay. So there is no net pressure on the sides. Here you go. Let's make a little bit longer. Let's see. Arrows. This one. Okay, better. All right. Can you picture that? On the top of that, we also have a pressure from the bottom. Because here the bottom is deeper than the top, this pressure here is going to be slightly higher than the pressure at the top. I am exaggerating, okay? Don't forget that I'm exaggerating here. And we can calculate it. What's going to be the value of pressure at different heights, at different depths? Let's do that. Okay. Okay, so that's going to be our example. Let's write it down. The pressure exerted by fluids on and off will always be normal to the surface, whether it is in the along the vertical direction, along the vertical or horizontal directions. Okay. So using the concept of pressure, force over volume, we now can determine the pressure that a given column of water exerts on you as you dive deeper, right? On you. as you dive deeper and deeper underwater, okay? And that's what the example is all about. Our first example is all about. Here you go. Find the pressure of a column of water of height h. And going back to the illustration here. Let's see if we can do that. No, okay. We're gonna go back to this illustration right in here. Okay, here you go. The column of water, right? Column of water of depth h and cross-sectional area A. Okay, so we just start with the concept, with the definition of pressure. Force, which is going to be the weight of the water column divided by area. Okay, look how mass help us find out this type of thing in a rather simple way. I really like it, this derivation, because it's a very simple way of finding out something that looks to be very difficult to calculate. The force to be given is going to be the mass of water in the column times the acceleration of gravity. Okay? And the mass of water is going to be the density of water times its volume, right? Now, do you see why we introduced you to the idea of density? Because we're using it right in here. But this volume that you see right in here can be written down in terms of the cross-sectional area of the cylinder, right? The cylinder of water times the depth, right? Can you picture that? Here you go. AH is this one right in here. Someone is trying to get it, right? Here you go. And this one here, how am I going to do that? Let's see. Yeah, let's leave this way. Okay, let's leave this way. And look at the nice thing that we found just by doing the simple calculation. We do not know what's the cross-sectional area of that cylinder, right? But we don't need to know. You don't need to know because this cross-sectional area of the cylinder cancels out in our calculations. Every now and then we find something like that in physics and math. You know, the parameter that we do not know cancels out. And now we have that the pressure due to the water or any liquid, doesn't have to be water, it's any liquid, is going to be directly proportional to the depth, directly proportional to the density, and directly proportional to the acceleration of gravity. Okay? It's linear with the depth. And we can go ahead, and write down some numerical values. If you're dealing with water, pure water, the density is 1,000 kilograms per cubic meter. If you're talking about the surface of the Earth, G is 10 meters, approximately 10 meters per second square, right? Here you go. And then what we end up having, 1,000 times 10 is 10 to the 4. 10 to the 4, right? When I put my H right in here in front of, and now we can see that we have kilograms meter per second square, right? Kilogram meter per second square. Let's see. And that's what we get here. Oh, by the way, we still have H here, right? And let me see if I can. Kilogram meter per second square is what? Is Newton, right? Newton per cubic meter. Is the unit okay or not? Right? Is this unit okay or not? Let's see if I can. Yeah, well, that's for water. We do know that a Pascal is Newton per square meter, right? That we do know. So let's write down in terms of Pascal. Here you go. Newton per square meter is Pascal. Consequently, Newton per cubic meter is going to be Pascal divided by meter. Is there anything wrong about this unit? We heard that the unit of pressure is the unit of Pascal, but instead it seems that we are getting Pascal per meter, right? Well, if you look at the equation here, nothing further from the truth, because we still have to consider the unit of H. The unit of H is in meter. Consequently, this unit upstairs is going to cancel out with the unit downstairs, right? So everything looks like correct here in terms of dimensional analysis. Okay. And recall that at sea level, the atmospheric pressure is 100 approximately, let's put it approximately 100,000 Pascal, which we call approximately 1 atmosphere. Okay, that's another unit of pressure, the atmosphere. Let us compare this number. Let us compare this number with the formula above. Okay, so here we go with the formula above and taking it, formula above, taking it at a depth at a depth of 10 meters. 10 meters, like that. So at a depth of 10 meters, what do we get? Because I don't need that anymore. At a depth of 10 meters, look what we're going to get. Don't forget we're doing that for water. 10 to the fifth, right? This meter cancel out with the meter. So you're getting a pressure due to the water alone of 100,000 Pascal, 1 atmosphere, which is approximately 1 atmosphere. So if you dive 10 meters deep, you're adding 1 atmosphere to the pressure. If you here you go. So if you dive 10 meters deep underwater, comma, we add 1 atmosphere of pressure due to the water alone. Due to the water alone. Okay? The net at this depth, the net pressure will be 1 atmosphere due to the water plus another atmosphere of pressure due to the air above. Finally, at 10 meters deep, at a depth of 10 meters, at a depth of 10 meters, the net pressure will be 2 atmospheres or 200,000 Pascal. Okay. Coincidence, right? I thought it was an interesting coincidence. Water at 10 meters having the same pressure as the atmospheric pressure of our atmosphere. Okay. Let's see, 9:53. And let's take a break. But before we take a break, let's take me attendance. Let me take attendance. Let's see. We have 17 students writing here. Let's see. Audrey, are you there?
I'm here.
Thank you, Audrey. Let's see. Wait. Next is Brianna Carrillo. Are you there, Brianna? I see Brianna. Oh, thank you. Next is Jazzy Castellano. Thank you, Jazzy. Next is Gabriel Contreras. I don't see Gabriel Contreras here, unfortunately. Okay, here go. Next is Molly. Thank you, Molly. Henry Kim.
I'm here.
Thank you. And by the way, an announcement, right? I'm teaching Physics 7 next semester. And just to remind you, right, I want to encourage you to join my Physics 7 course. My classes are filling up quickly, and I have more than 20 students registered for Physics 7. And I want to encourage you to, if you haven't done that, I want to encourage you to register for this course, which is Physics 7, which is a continuation of Physics 6. Okay, let's put a note here. My notes, because I want to encourage, for the spring, I want to encourage you to register for the continuation of this course Physics 7, which is being offered in the spring. Yeah, that's right. In the spring, I think Physics 7 is far more interesting course. I think Physics 7 is a far more interesting course than Physics 6. But it's more difficult too, right? But it's more difficult too. It involves the physics of the 19th and 20th centuries, okay? So what we're studying here in this course is the physics that start on the 15th, 16th century, all the way up to the 18th, 19th century. That's what Physics 6 is all about. Now, Physics 7 is the most recent body of knowledge that we accumulated in physics, okay? And Physics, let's see, spring 2025, right? Spring 2025. And let's see, Ruth, are you there, Ruth? I can see Ruth is here. Okay, thank you. Next is Noemi. Hi, Noemi. Danae Miller. Hello, Danae. Are you there? Okay, must be away from her computer. Ramon.
Here.
Thank you, Ramon. Next, Taylor Forn.
I'm here.
Thank you, Taylor. Stephanie Ramos. Stephanie Ramos, I don't see Stephanie here. Next is Jeremiah. Jeremiah already told me he is here, right? Yeah. Thank you, Jeremiah. Sean Rosario. Oh, okay. Thank you, Danae. Sean. Let's see. Okay, next, Ali. Ali Standard.
I'm here, Professor.
Thank you. Jason Strait.
I'm here, Professor.
Thank you. Elena. Good. Jason Valadares.
Here.
Thank you. Laurel Williams. Laurel, I don't see Laurel, right? So we go. Laurel Williams. And next is Nohamian. I don't see Nohamian either. And Alia Zavala. Hello, Alia, are you there? I'm gonna put a star here. Let's see how many students we get. Okay, thank you, Alia. Let me add you here. 17. Yeah, we have 18. We're gonna make it lecture. Okay, it's gonna be part of the lecture since we are not meeting on the 9th, right? So the 11th is going to be final exam. Okay. It's 9:59 right now. Any questions? Okay. Okay, so let's go for our break. Break 10 a.m. To 10:15 a.m. Okay, I see you in 15 minutes. Okay, I'm back here. Let's go back to we're almost done with that. There you go. Pressure. Okay. So we covered the definition of pressure. And then pressure and depth in a static fluid. Don't forget, we're talking about static fluid, okay? If there is a current, a water current, then there will be an additional term in there that is going to either add to the pressure or subtract the pressure depending on the direction of the fluid is flowing, okay? So that's why, I italicize static fluid. Okay, we're talking about static fluid. The last thing that we want to cover in this chapter is the Archimedes principle. Something that was discovered by Archimedes himself at his time. Man, by the way, Archimedes, I would say that Archimedes is the greatest genius in the history of mankind. I would say that. Okay, what he managed to do, it's impressive what he managed to do. I would say here, his contributions was far-reaching than that of Einstein, I would say, than that of Galileo, than that of Newton himself. So, and here we are going to study only part of his contributions. Okay, even today is important to note that even today people are discovering which which other contributions that Archimedes made, and they managed to find some of his journals at the time. And there are many more journals of Archimedes missing from the history. Most likely it was, it was destroyed throughout the times. And whatever we know about Archimedes is, I would say, is less than what his actual contributions was, right? His actual contributions were. Okay, so let's talk about this principle, Archimedes' principle that's applied to fluid. Remember that pressure increases with depth. Keep that in mind. Consequently, pressure is going to be higher at lower regions of an object if compared with higher regions. Okay? So for the human body, if you're upright underwater, the water pressure at your feet will be higher than the water pressure at your head, right? Let's put this one. Then the will be higher than the water pressure at your head. Make sense? And I already showed you an illustration. Okay, this difference in pressure and this differential in pressure results in a net upward pressure that produces what we call a buoyant force. Okay, that's why you feel lighter underwater, because of the higher pressure under our feet. That's why we feel, and this phenomenon is used by NASA to train the astronauts in that neutral buoyancy facility. They call it WET, W-E-T, weightlessness environmental training. Let's take a look. Okay, so this buoyancy force, something discovered by Archimedes himself, is used today by NASA. Why I can't get this thing closed here? Okay, that's. Oh man, see that? Okay, I don't know what this thing is. Cannot close, but that's okay. Let's get this other one here. Weightlessness, environment. Oh, they call it training, not testing. Training facility, right? Neutral buoyancy facilities for spacewalk training. Not only NASA has that the Vomit Comet airplane that we fly a parabolic trajectories in the sky to make you feel weightless, but NASA also used this huge swimming pool to simulate some aspects of zero gravity. And a colleague of mine from NASA who became an astronaut, by the way, he had an incident in this facility. His name is Leland Melvin. He flew twice in the space station. Okay, building on a mission, right? Neutral buoyancy facility for spacewalk training. See that? So NASA is using this facility. He's using Archimedes' principle to simulate some aspects of zero gravity. Here's the swimming pool. Here's the astronaut with the spacesuit. It's not just the astronaut that's there is the spacesuit, but we also have those divers nearby him in case there is an emergency, and it has happened. Okay, think about those astronauts when they are training here in this facility. Not only they have the spacesuit on them, but they also have weights, metal pieces in their spacesuit to balance them underwater and become what we call neutrally buoyant, to simulate certain aspects of zero gravity. And NASA put mock-ups of some equipment in there, like the Hubble Space Telescope, okay? So the astronaut goes underwater and they become familiarized with the space hardware that they are going to find in space. They're going to, for instance, work, right? When astronauts went to fix the Hubble Space Telescope, they had to become familiarized with every piece of the Hubble Space Telescope. And NASA submerged a mock-up of the Hubble Space Telescope underwater here. Okay, so let's talk about that. Let's go back to our, let's see here. Okay. Let's go back here to our topic. And also I want to show you this. Okay, you saw that before, right? Here you go. The block underwater is subjected to this air pressure and the water pressure at the top. But sideways is also subjected to this pressure. Okay, on both sides. The pressure is this type of funny force that exerts this force normal to the surface of an object. So sideways, the net force is going to be zero, right? Sideways. But in the vertical direction, what happens? In the vertical direction, not only we have a pressure from the top, but you have a pressure from the bottom. But because the pressure on the bottom is higher than the pressure at the top, we are going to have a net force that's going to be upwards. This net force we call the buoyant force. And that's why we feel lighter underwater, because we have this pressure upwards on us. Okay, that's overcoming the downward pressure that comes from the top. And the question is, how can we quantify this buoyant force? It's possible to quantify this buoyant force. It's not difficult, okay? And I'm going to walk you through how can we quantify this qualitative idea of buoyant force. So far, it's just a qualitative idea that I gave to you, but let's find out. It's not difficult, okay? Here you go. We can quantify it just by working out an example. But let's see. Here you go. But before we go into the example, let me formulate the buoyant principle, the Archimedes principle. Here you go. Here's the Archimedes principle. When you submerge an object completely underwater, the object displaces its own volume of water. Okay? Makes sense. It must make sense, right? Because no, the water cannot occupy the same space that the object is occupying, right? They cannot be collocated simultaneously, right? They cannot be collocated just, water is not like a ghost, right? Ghosts can be collocated with a solid object, but not water, not anything in the physical world. Okay, so first, Archimedes starts thinking about that. And the first thing that he realized is that the liquid or the water, the fluid, cannot be collocated with any other object. Right now, the air that's surrounding us is not collocated with our body, okay? And then he came up with the next principle. After recognizing this, he was able to formulate what we call Archimedes' principle. What Archimedes concluded at this time is that was the following concluded this time is the following. The following. The buoyant force is equal to the weight of the volume of the displaced fluid. Notice that I didn't say weight of the volume of the water. No. I said the weight of the volume displaced by the fluid, right? Can be any fluid, not just water. Can be the air that's surrounding us. At this very moment, we are displacing some air. The amount of air that we're displacing is roughly the volume of the human body. And the weight of this air that you are displacing is exerting also a buoyant force on us. A tiny buoyant force. That's not enough to float here in the air, okay? It's the same applies to the water fluid. And we can exemplify, we can come up with an example of this principle. Here you go, example of Archimedes' principle. A solid object with 1 cubic meter of volume is completely a solid object with a volume with a volume of 1 cubic meter, right? Let's put it with a volume of 1 cubic meter is completely submerged. It's completely underwater here. Using the Archimedes principle, determine the value of the buoyant force applied to this object, right? Okay, so let's write it down. Since the object has a 1 cubic meter of volume, it also means that it displaces 1 cubic meter of water, right? So all we have to do is to determine. So all we have to do is to determine the weight of this volume of displaced water. Okay, and it's not difficult to do that. First, we have to calculate the mass of displaced water. In order to calculate the weight of the displaced water, we have to calculate the mass of the displaced water, right? So here you go. Here you go. Weight of displaced water is going to be the mass of the displaced water. I'm going to use this one here. The mass of the displaced water times the acceleration of gravity, right? That's what we have to find out. So far, we do not know what's the mass of the displaced water. Let's put that in boldface. Okay? And now we go ahead, calculate the mass of the displaced water. We do not know the mass of the displaced water, but we do know the density of the water, right? The mass of the displaced water is going to be the density of the water times the volume, the displaced volume. Once you realize that, it's rather easy to, here you go, density of displaced water, density of the water, 1,000 kilograms per cubic meter, right? And already told you here in the problem, right? The problem already gives you the amount of volume that's displaced, 1 cubic meter. The volume of the object is going to be the volume of the displaced water. And what we get 1,000 kilograms. 1,000 kilograms, here you go. And now we have to calculate the weight of the displaced water. Is going to be 1,000 kilograms times G, and we get 10,000 newtons. approximately 10 meters per second square. Second square, not second cube. Here. That turns out to be 10,000 newtons. 10,000 newtons. Okay. Consequently, don't forget the buoyant force that I'm going to denote by the letter B is going to be equal to the weight of the displaced fluid, which is 10,000 newtons. So this object now has this other force acting on this object, which is going to be an upward force. All right, here you go. I'm submerging the object. I'm looking at the level of the water, and when I completely submerge the object, we notice that there is some water displaced. Don't forget, this is your static fluid, right? Here you go. Now the level is higher, and when we submerge the object, we're going to have this buoyant force and the weight of the object. That's the free body diagram of the object, right? And we're going to come up and now we can use this knowledge to figure out which object is going to sink, which object is going to float, and which object, what are the conditions, not which object, but what are the conditions for the object to remain under neutral buoyancy. The conditions for the object to sink, the conditions for the object to float, and the conditions for the object to remain neutrally buoyant. And neutrally buoyant means at a single spot underwater, okay? Fishes are very good at doing that. To be neutrally buoyant fishes, yeah? They are masters of doing that. And the astronauts, when they go underwater, they have to achieve this neutral buoyancy condition to train for spacewalks. Okay? So, well, it's not difficult to figure that out, okay? Okay, so here you go. All you have to do is to look at the free body diagram. A completely submerged object underwater having a volume B will sink whenever the net force applied to it is downwards. Okay, so here you go. Here is the situation in which you have a sinking object. I'm going to copy and paste it there in my notes. Here you go. Copy and paste it. So here you go. The weight of the object must be greater than the buoyant force, right? So that's gonna be the condition. Here you go. The mathematical condition is going to be this one here, greater than 0. Here you go. Don't forget, this is the mass of the object. It's the acceleration gravity of the object. And we can work out the next step. Here you go. mg minus b is going to be what? The mass of the object times acceleration of gravity minus the mass of the displaced volume of the water times g, right? When this relationship is greater than 0, then we have a sinking object. We didn't quite get there yet. Okay, because we suppose that you do not know the masses involved here, right? You do know what G is on the surface of the water, right? On the surface of the earth, right? So here you go. Like it here. Okay. I can put the G in evidence. Let's put the G in evidence. Like that. When we put the G in evidence, we can cancel out the G. We didn't quite get there yet, but we're going to get there. It's not going to be equality because this term here without the G is not an equality, right? It's going to be something else. I'm going to put let's see, this sign here, narrow, right? So now we have a simpler condition, right? And that's the condition that we have to work out. And what can we do? We can write down the mass in terms of the density and the volume of the object, right? Do you agree with that? Here you go. Can be written in terms of the density and the volume. Now you see how important the concept of density is. We do not have a G here. Okay, density of the object times this volume is its mass. Density of the water times the density of displaced fluid is going to be the mass of the displaced water. Now let's continue it downstairs. Let's not forget that the volume of the displaced fluid is going to be equal to the volume of the object, of the submerged object, right? Here you go. And now we can simplify this equation even further, right? Here you go. This V displaced becomes V. And now we put the V in evidence. And we further simplify the equation. Here you go. And this term here must be greater than 0 for the object to sink. Here you go. Now that's the new condition, right? So what we have here? We have here that for the object to sink, its density must be greater than the density of the water or the density of the fluid. Okay? That's the condition that we got. And what about for floating? Okay? Okay, we can repeat the above for a floating object. An object that floats. For an object to float, once it is completely submerged in water, okay, comma, the buoyant force must be greater than its weight. Here's the condition. Okay, and let's see. Okay, that's the condition. Free body diagram, right? When the buoyant force is greater than the weight, the object will tend to move upwards. There will be a net force upwards, and the object will tend to move upwards, right? So that's the one. Let's see. Condition for an object to float. It must move upwards. To float. Okay, and all you have to do now is repeat what we did here, right? But instead of greater than zero, you must have less than zero. You repeat every step here, and what you get at the end is going to be that the density of the object must be less than the density of water. Okay? Condition for floating, just like your styrofoam block, your block of styrofoam. Your block of styrofoam has a density smaller than the density of water. That's how it ends up floating. Okay, and finally, what about neutrally buoyant? Buoyant. Like I said, for the neutrally buoyant condition. Let's see here. Neutrally buoyant condition. Here you go. The weight must be equal to the buoyant force. Okay. So I'm going to put here. I'm going to put the condition. So it's not by itself, right? You have to follow. The original condition is this one here for floating and for remaining neutrally buoyant, just like the astronauts do. The density of the object must be equal to the density of the fluid. And that's a condition that our human bodies can achieve as well, okay? And I'm gonna get that other one. Here you go. I wanna talk a little bit more about buoyancy, neutrally buoyant condition. Neutrally buoyant. Like that. Neutrally buoyant. Density of water equal to the density of the object, okay? Okay, here you go. The human body is what? 70% made of water, right? Let's take a look. Whoa. Let's see, where is this one here? Water. Water content of human body, of the human body. Something around 60% by weight. Human body is made up of approximately 60% of water by the weight. So our body has more or less the can have more or less the density of water. Here you go, brain, 95% of water, lungs, 90%, blood, 83%. See that bones, 22% of water, skin, 64%, kidneys, 79% of water, right? We have lots of water in the human body. 60% of it is by weight, is water by weight. Okay. Because 60% of the human body is made of water, we have a density that is very close to this fluid. Okay? Actually, because of the lungs, the density of the human body can be varied, slightly if we take air in, our density decreases. However, if we expire, right? Inspiration and expiration, right? Our density increases, right? Remember, air is what? 1,000 times less dense than water. Remember that? It's almost 1,000 times less dense than water. It's almost 1,000 times less dense than water, right? 1.2 times 10 to minus 3 grams per cc versus 1 gram per cc, right? We saw that before in that table. Because of this ability to inspire and expire, we can vary our density. And that is something that we can readily experience in the swimming pool, on a swimming pool. Swimming pool, okay? Just float above the water and start by taking in air into the lungs. Okay. You will notice that you will move upwards. You will float. However, when you empty your lungs, you will sink, right? Into the pool. So you can experience that by doing this exercise, okay? But be careful if you're going to do that. Be careful, right? Don't want you to drown. If you do this exercise, make sure you don't drown. Okay, any questions? Let's see how we're going here. 15 students. And let's take another break. That's all you have for chapter 11. That's all we have for chapter 11. Okay, and let's have a break. Let's have a break now. And when we return, we start covering chapter 16. Let's take a look. Let's take a look at the book here. I gotta get inside the Wiley Plus again. Wiley Plus. Okay, log in. Go book. Wiley source, course source. Let's see, book launch. Fluids, right? We finish what we want to cover on fluids. Well, 12 and 13, I usually don't cover it. And 14, we don't have either, nor 15. But I usually have time to cover here waves, an important concept. Okay, let's see how far we can go today in this chapter 16. We're done this chapter 11. And when we return, we will start chapter 16. Okay. Let's see how much we can cover for the exam. Break 10:55 a.m. to 11:10 a.m. Any questions? All right, so I see you in 10 minutes, in 15 minutes. Let's play. Now let's get into chapter 16. Okay. I don't. Let's see how far we go, and then I adjust here the material for the final exam. Okay. We cover. Okay, so let's see. So far, exam is chapters 8, 9, 10, and 11. 8, 9, 10, 11. And let's see how far we can go into chapter 16. So far, the material for the final exam are chapters, let's see, 1 through 11. And okay, chapters that didn't show up, the chapters that did not show up so far in the partial exams are 8 through 11. And let's see how far we can go. Let us see how far we can go in chapter 16. Okay. Chapter 16. Okay. That's what we have now. Okay, so what chapter 16 is what? Waves, okay? Chapter 16, waves and sound. There's a difference. There is a difference between point particles, let's see, material objects, right? Material objects and waves. There's an important difference in waves. Waves is like transport of energy, which, by the way, has no mass whatsoever. Okay, so waves are immaterial. Is a concept. Is a concept that has no mass and is closely related to energy. Energy too has no mass whatsoever. So that's what we call the duality between particle and energy, right? The so-called particle wave duality. One has mass, the other doesn't. And this is a very powerful abstract. Okay, this is a very powerful concept. Although abstract, although extremely abstract and generic, okay, and generic, it is used in physics to explain certain real-life phenomena. Okay, like I said before, a wave is energy that propagates along a medium. Let's see what types of waves do we have. There's a bunch of waves. There's a bunch of things that can be described as a wave. Okay, types of waves. The most common one. Let's see. Okay, here we go. The most common type of wave is the one that propagates along a string or a coil. We pluck a string and we see that vibration in the string. But in reality, what's happening is that energy is being transported along the string, which is a medium, from one point to another, back and forth in the string, okay? Although you have a vibration, when, let's see, when you pluck a string, you put it to vibrate. In addition to the vibration of this material object, the string, you also have energy that is being transported from one end of the string to the other. One end of the string to the other, right? Back and forth. You know, back and forth. If the ends of the string are at the ends of this, no, did I say spring? String, okay? Of the string are attached, are fixed or fixed. Okay? So in addition to the material medium, there is also some energy that's propagating in the medium. In this case, it is the medium itself is the string. Water waves is just another example is another example of wave. You have the medium, the material medium, which is the water. Material medium, which is the water, and within this medium, energy is transported. Okay, this energy is let's say verified as a wave. Okay, what else? Sound. Sound is another type of wave. Sound. This type of wave propagate in any material medium. Air, metals, gas, any gas. But, we do know that sound does not propagate in vacuum, right? We know that. Okay, let me give you another example. Earthquakes. We have the waves of the earthquake that propagate. It has energy. Earthquakes together with the crust of the earth, we also have energy that propagates along the earth's crust. And this energy and this wave we also have a wave, right? And this wave has enough energy to destroy buildings, right? Destroy buildings. And the ultimate wave, well, let me see. Okay, before we go to the ultimate wave, let's talk about another very important wave that we're going to study in detail next semester. Light. Light is also a wave. Light is also a wave. More specifically, an electromagnetic wave made of electric and magnetic fields. That's why it's called electromagnetic. Light does not require a material medium to propagate. It can propagate in vacuum. It can propagate in vacuum. Okay. This wave has energy that can be converted to do some important work. Okay, like a photovoltaic cell. Photovoltaic cell can convert light into electric energy, right? Photovoltaic cell or a solar cell, photovoltaic or solar cell. And here you go, the ultimate type of wave that was finally discovered, which was predicted by Einstein 100 years ago, are the gravitational waves. We finally detected it. Gravitational waves initially predicted by Einstein more than 100 years ago. more than 100 years ago, comma, which was finally detected recently. Let's see when they detected gravity waves. You go gravity wave. Gravity waves in space. Okay, here you go. Gravitational waves are ripples in the fabric of space-time that travel at the speed of light and are caused by some of the most violent events in the universe. Okay, when gravity waves were detected, LIGO did that recently, and they're talking about the Nobel Prize in physics. Okay, here you go. Albert Einstein predicted the existence of gravity waves 1916. Let's see, the European Space Agency. It doesn't say when LIGO detected the gravity, but it was recent. Let's see, gravitational waves. When was gravity waves? When was gravity wave detected for the first time? Right, detected for the first time. Here you go. September 2015. 14th of September 2015. Okay. It took 100 years. Einstein predicted that back in 1916, right? So 100 years, 101 years. So those are the different types of waves. The simplest of them, the simplest of all, is this one here. A wave in a string. The simplest one to visualize. Okay? Water waves too are very simple to visualize. What you have to know about a wave, in order to create a wave, you must disturb the medium it propagates. It propagates on. We have a string. We disturb the string by plucking it, and then you generate a wave that propagates back and forth. Okay. Okay. The same thing for the body of water. For a body of water, right? For instance, if you pluck your finger at the surface of a body of water, you disturb the water and create a wave that will propagate away from the point of disturbance. The water wave itself will oscillate in the perpendicular. The water wave itself will oscillate in the perpendicular distance, up and down, up and down. Okay? But then there are waves that oscillate along the longitudinal direction of propagation. Okay, so we have that gives rise to two types of wave that gives rise to two types of waves. You know, transversal waves. But that's transversal with respect to the direction of propagation, okay? Transversal waves. Example of transversal waves. Waves along a string, here you go. Waves along a coil that moves up and down. Light waves of electromagnetic waves. The electric and magnetic field oscillates perpendicular to the direction of propagation. Right? The waves in a string too, you can see it moving up and down, right? When you pluck a string, but the waves is actually moving the horizontal direction, back and forth, whenever the two strings are attached. That's how you should visualize it. Water waves, yeah, they are transversal waves as well. Some types of waves, not everyone, but some types of waves associated with earthquakes. Okay, for in the case of earthquake, we have both transverse and longitudinal waves. And then we have longitudinal waves. This you have to memorize. Okay, what is longitudinal wave? What is transverse wave? You know, the only way is for you to memorize Another way would be to look into the equations of a wave, which are rather complicated, okay? The equations of the wave tells you a story of whether the wave is transversal or longitudinal. Sound waves. Sound waves are longitudinal waves. And let me tell you how sound waves work, okay? The sound waves is like, behaves just like a coil. Behaves. Sound waves, which behaves, which behave, right? Just like a coil that's compressed and distended. Okay? That's how you should picture a sound wave. A coil, right? A wave in a coil that's compressed and distended. Some types of waves associated with earthquakes. Okay, let's take a look at the internet, right? Earthquake waves. Types of earthquake waves. Here you go. Oh, earthquake. And they said, yeah, here you go. PNS waves. Okay, earth waves. I don't want earthquake waves. Earthquake waves. Here you go. There are surface waves and there are body waves. Okay, body waves travel through the Earth's interior, including P waves and S waves. P waves are called primary waves, are the first to arrive at seismic recording station, are the fastest type of waves. S waves are called secondary waves, are the second fastest wave. Okay, surface waves. Most of the ground motion during earthquakes cause most of the ground motion. The two types of surface waves are love waves and Rayleigh waves. Rayleigh wave as lowest, but they don't say anything about, let's see, here you go. Here you go. This wave right in here is a transversal wave. You see? The transversal wave causes disturbance in the vertical direction, in the transversal direction that the wave is propagating. The wave is propagated from the left to the right. And we have this disturbance transversal to the propagation of the wave. Okay, here you go, even better. It's called the surface wave, S wave, secondary waves. Not surface wave, it's a secondary wave. And then we have the P wave. It's like a compression, compresses back and forth, and in addition to compress back and forth, it also moves along. Okay, the compression and the distension is, of course, along the direction of propagation. Okay, and we're going to study one-dimensional wave. We have two-dimensional waves as well, but I want to stick to one-dimensional wave. Okay, there are 1D waves, 2D waves, 1D waves, 2D waves, and 3D waves, right? 3D waves, but we will study, and we will study the simplest one. The simplest one, 1D wave. 1D wave. Okay, what you have to know, the most generic equation of a wave is the following. That's how we can mathematically write down about a wave. There is an equation. There is a mathematical equation that we can write about a wave. Okay, sine waves and cosine waves, can be written down y equal to whatever sine in a function. Okay. Now, what else we can tell? I can tell you about that. There are forward propagating waves and backward propagating waves. Okay, the forward propagating waves can be written mathematically, or it can be modeled, not written, but can be modeled, can be mathematically modeled as following. Mathematically modeled as following, Okay, so here we go. Y, right? Y is the expression for the wave. X is a function, the wave is a function of X, but it's a function of T as well, okay? And we is going to be written like that, X minus VT, okay? It's a function of X and T, yes, but it's specifically a function of X minus VT. That's a forward propagating wave. A backward propagating wave is slightly different. It's slightly different. Okay? Where you have a negative sign here, it becomes positive. V here is the speed of the wave. Examples. Examples of forward and backward propagating waves. The type of wave that you're going to see most of the time, is a sine or cosine wave. Okay, so here you go. We can put y naught, okay? That's the amplitude of the wave. And then here goes sinusoidal wave, kx. I'm going to put kx minus vt. Let's see how I'm going to do that. Omega, yeah, it's going to be omega vt. No. Let's see. Kx. Okay, yeah, it's like that. Is the k parameter. I'm going to tell you what this k parameter is all about. And this k parameter is multiplied by the x minus vt, okay? I'm going to tell you about this k parameter. That's the new one. V is the speed of the wave. T is the independent variable time for the time, and x is also the independent variable for the position of the wave. Okay. So this equation that you see right there is just a transversal wave that propagates from the left to the right. It goes like that, and it oscillates back and forth like a sine wave, okay? And as the wave propagates, it looks like a sine wave. Let me see if I can get you a very nice illustration. Not here. I'm going to illustrate this summer. What happened here? Okay, that's LA Harbor. Let's go elsewhere. I taught this course in the summer, and we have must be here. Let's see, student syllabus to travel reservations, homework. Okay, doesn't look like it's here. Let me see if it is here. Uniform motion, sample solutions. Um, yeah, it's not here. Let me see if it's elsewhere. 23. Let's see if it's here. Simulations, right in here. Okay. Simulation, sound waves, oscillation must be here. Let's check if it's here. No. Maybe this one. No. Must be here. I'm going to show you an illustration of a standing wave sound. Let's see what. Okay, here you go. I got it. Okay. So here you go. Here's as an example of a sinusoidal wave. At a given instant of time, you're going to see the wave right just like that, like a sine wave. Let's see, 1, 2, 3, 4. Yeah, good. Amplitude here of this wave is 0.4 meters, okay? Amplitude is the largest distance from the position of equilibrium, which is the zero, to the peak of the wave. It's 0.4 downwards, 0.4 upwards, okay? Right now, the thing is just a snapshot of my sinusoidal wave. But if we put it to, let's see, I'm going to put it time t equal to 0, right? If you put it at time t equal to 0, the wave is right in here. Now I'm going to put this wave to move. Let's see how you do it. 0.2, time t equal to 0.2. Now I move very little. Okay, let's move a little bit more, okay? 0.5, let's see if we can move it. 0.5. It's moving backwards. This wave is moving backwards. Do you see that? Do you notice that? No, let's put back at 0. 1 second. See that? The wave is moving backwards, right? And this is something is moving backwards because I put a plus sign right in here in this equation. Okay? Is a k parameter right in here, x plus vt. Okay? So here you go. Keep on moving. The wave is moving backwards. See that? 5, 6, 7, 8, 9, 10, right? And I can talk about the parameter of the wave. I didn't tell you the parameter. Let's see if I have a forward propagating wave, standing wave. Yeah, strange. I don't have a. Okay, so that's the transversal wave. I'm going to show you a longitudinal wave. Okay, here's the case of a longitudinal wave, which is a very good model for the sound. This wave is a forward propagating wave. See here? Forward propagating wave because we have a negative sign there. The sound is just a wave that propagates in air. Each of those little dots that you see right in here represents an air molecule. This bigger dot that you see here, is supposed to be smaller. Okay, I put it larger so my students could see that this dot is moving back and forth. It's not going with the wave itself, but the media is just oscillating back and forth. What seems to be moving from the left to the right is the wave itself. Let's take a look. Time t equal to 0. Here you go. Here's my wave. Let's see. 1 second. Didn't do anything. Let's see. 0.2 seconds. Okay. So I went too fast. Okay, let's start here. 0. 0.1 second. Look what happens to those compressions here. Here, the compression and the harification of the wave, right? The distension and the compression. Watch what happened. Okay, going back to 0. Time t equal to 0. 0.1, 0.2. Watch the compression. The compression is moving from the left to the right. 0.3, 0.4. Do you see? And now I want you to pay attention to this big dot that you see right in here. This big dot is not moving from the left to the right. No. This big dot is just oscillating back and forth. Just like transversal wave, the particles of the transversal wave moves up and down, the particles of the transversal wave moves back and forth in the direction of propagation of the wave, okay? So 0.4, 0.5, 0.6, 0.7, right? 0.8, 0.9, 1, right? Now I can go ahead and undo. And we are going to see that the wave is going to propagate to the back, right? Because I am undoing it. But pay attention to this big dot here. Okay. Now redo it. Here you go. This big dot is just oscillating back and forth. But the wave is seen to be moving from the left to the right. Oops, what happened here? Okay, better. Better. Okay. Now you have an idea how transversal waves and longitudinal waves work. Look like. Work now, but look like. Now let's talk about the components of a wave. Components of a wave. Okay. A wave has amplitude. One, amplitude. Okay. The distance from the point of equilibrium to the crest or valley of the wave. What you saw in that sinusoidal wave is that we have a crest, the crest of the wave, right? And the valley of the wave. At the top of the wave is the crest. The distance, the midway distance here is the point of equilibrium. And the distance from the equilibrium to the crest is going to be the amplitude. Whether to the crest, whether it's to the valley, is going to be the amplitude. Okay? This is the most, I'm going to write that down here. A sinusoidal wave, sinusoidal, or cosinusoidal wave, are the most important types of waves. Okay, there are all sorts of waves out there, but the sinusoidal waves are the most, and cosinusoidal waves are the most important type one of waves. They are the most important type. They are the most important types because any wave can be written in terms of a linear combination of sinusoidal and cosinusoidal, right? Waves, sinusoidal, yeah, that's why. So any wave can be written down by linear combination. I mean a summation. In other words, you know, why? But can be written down as a summation. Here you go. Summation. Why not sine of, let's say, a sub I x minus vt, okay? Where I goes from 1 to n. There's a linear combination of sinusoidal waves. Any wave can be written down like that. If it's a forward propagation wave, it's like that. If it is a backward propagation wave, it's going to be like that. I still didn't tell you what the K parameter is, okay? I'm gonna tell you right now. Forward, backward, okay? Amplitude, the distance from the point of equilibrium to the crest of the wave. That's the amplitude here of my wave. What else? Speed. Okay. Speed of the wave. Okay. The speed a wave propagates. Okay. An electromagnetic wave propagates at the speed of the light and in the vacuum. 300,000 kilometers per second is the fastest thing that we know of. Okay. Wavelengths. Our wave has wavelengths too. Here you go. Our wave has wavelengths as well. Here you go. Distance. What's the wavelength? The wavelength is the distance between consecutive peaks or valleys. Okay. So let me show you here. The distance from this peak to this peak is a wavelength. And I can adjust this wavelength for you, okay? Right now, according to my simulation, the position right in here of this peak is around 14.83. Can you write that down? 14.83. And the position of this peak, don't forget for 14.83 meters, right? And the position of this peak, let's see here, it's 35.02, okay? Which is approximately 20 meters, okay? And this wavelength is right in here in my table. Do you see I put 20? Lambda stands for the wavelength. It's a symbol for the wavelength, the lambda Greek letter. Let me put here in the Greek letter format. So lambda symbol, yeah, here you go. See here, the Greek letter lambda is the L in Greek. It is corresponding L letter in Greek. And I can change the simulation here. We can change the wavelength of this wave. I'm gonna shorten it up. So you are going to see, instead of 20 meters, I'm gonna put it 15 meters. See that? Now the wave is more compact, right? This peak is around 10 meters, 9.5, almost 10. This other peak is around, should be around 25, okay? Yeah, it's 25. So this distance here is 50 meters. That means 10 meters. You're going to see that the wave is going to become compressed, right? See that? Let's put 30 meters for the wavelengths. Peak to peak. Oh, now we cannot even see. Oh, but we can see that the valley to the valley is going to be 30 meters. Here is 10, here is 30. See that? Distance of peak to peak. Now that I told you what the wavelength is, I can tell you what this K value is all about. The K value, the so-called K value, or wave number, we call it wave number, is related to the wavelengths as, K equal to, I'm going to write down, here's my formula, here you go, is inversely proportional to the wavelengths, okay? K is 2 pi, it's just like, 2 pi over lambda. Okay, that's what K is all about. Inversely proportional to the wavelength. Crests, right? The wave has a crest. Nodes, positions of equilibrium. Nodes. So here you go. You already know that. I already introduced you to here's the crest. Here's a valley. Here's a node. A point of the wave that intersects the position of equilibrium. Okay, so but a wave has a period as well. A wave has a period. Period T. Okay. This is the period of oscillation of a point along the wave. Okay. That is a relationship between the speed of the wave, the wavelengths, its wavelengths, and period. Its wavelengths and period. Okay, here you go. The speed of the wave v is going to be equal to the wavelengths. It's not difficult to memorize that. Divided by the period. Every wave, obeys this relationship. And this period here, the inverse of the period, can be written down as the frequency of the wave. Do you remember that? We saw that in simple harmonic motion. Every wave obeys the above relationship. Every wave obeys the above relationship. Right? Lambda times frequency. Okay, and now let's go back to our wave equation here. What you see right here is in reality, right? Something like that. 2 pi over lambda, like that, x minus vt. And note that the x here has the same unit as the lambda, right? That's because whatever goes inside here, the sign function, the argument of the function, must be unitless, cannot have any unit. Vt has the same unit as x. So when Vt is divided by lambda, we have an argument that has no unit whatsoever. And you can take the sign of that, okay? Now, what else can I tell you? Okay. Already told you that forward wave, right? Forward wave can be written as, here you go. Here's my equation for a forward wave. Waves can also be reflected from an obstacle. Okay, from an obstacle. And a reflected wave can be written as, here you go. But, depending on the obstacle, can be reflected from an obstacle. And depending on the obstacle, even better, a wave can also be reflected from a fixed point of a string, okay, of a string, right? Get one end of the string fixed here, and you have a string, right? A wave is propagated towards this fixed point, okay? Fixed point of the string, and it can be, and its wave and its equation, right, can be written as What happens when a wave is reflected at a fixed point? Okay, it inverts. Its amplitude gets inverted. Not only its amplitude gets inverted, but now the wave must propagate backwards, right? I'm going to write that down here, reflected wave. And here I'm going to write down incident wave. Incident wave. Can you picture that? Okay, reflected wave looks like that. What if the end of the wave is loose, right? Well, there will also be a reflected wave, but the wave is not going to be inverted in amplitude. Okay, you're going to propagate in the opposite direction, but not it. But its amplitude will remain in the same direction. Okay. The best way is to look. Oh, 1201 already. Okay. So we can stop now, right? Here you go. Nature of the waves. I talked to you about periodic waves. We covered that. The speed of a wave on a string. Oh yeah, the speed of a wave in a string is depend. We didn't cover that. Okay, let's skip that. Mathematical description of a wave. I did that, and I didn't do the nature of sound. But oh, I told you the nature of sound is a longitudinal wave. Longitudinal wave. Okay. So that's what we covered. Thank you very much for being here. It was really nice to be with you all here, and I hope we can continue this course next semester in the spring. Okay? And then I see you next week for the final exam. And by the way, the topics for the final exam, let's see, is in my previous. Let's see, the review, right? The review for the final exam. Check the review for the review of my final exam. Yeah, check the notes of the previous years. Okay, I have the review for the final exam there. Unfortunately, we can't review it now because we run out of time. Okay. So I see you next Wednesday, a week from now, for the final exam. So let's see, we have, thank you all, folks.
Professor, I have a quick question.
Yeah,
Do we meet at 9 or 10? Because the syllabus says 10 to 12 for the final exam.
yeah, for the final,
Uh-huh.
we meet at 10.
10. Okay.
Okay,
Got it. Thank you.
okay, welcome.
Thank you, Professor. See you
Welcome.
Wednesday.
See you later, see you next week.
Bye, Professor. Thank you.
Welcome. Everybody. Ok, a gente precisa sair agora, né? Vou pegar o carro. Ai, pegar o carro. Deixa eu desconectar aqui. Ok, vamos ver. Estou reencaminhando sua mensagem. Lembrei de que está atualmente acompanhando. Ah, ok, ela poder responder. Ok, ótimo.
Quem é esse aí?
O Antônio respondeu. Ah, o André respondeu. O André respondeu. É a Jaqueline, né? A mesma que entramos em contato anteriormente.
Line.
É. Ok, o L Plus. Não sei. Ah, Jaqueline respondeu já. Ok. Ok, então a gente vai precisar falar com o Abib. Ah, essa contrapartida a gente usa do jeito que a gente quiser, foi isso que ela falou. Agora, das subvenções, precisa falar com o nome dele? Abib? Abib, é. Que horas a movida fecha?
Acho que até 6.
6. Ok. E tem que ir agora mesmo. Agora não bobeira, não.
Eu não sei se lá fora tá.
Parece que tá frio, não parece? Ai, ai, tô com diarreia. Hã? Hã?
Deixa eu botar aqui uma.
Posso abrir? Posso abrir? Ok, ok. Olha lá, né?
Não tem como fazer podre. Não é cheiroso?
O que você quer que eu faça? Não tem nada que eu possa fazer a esse respeito.
Eu também faço podre.
Não.
A diferença é que eu faço alguma coisa.
Lá fora?
É?
Lá fora?
Irmão, não está aqui. Não chegou uma também.
Boa. Não sei, não sei. A minha não vou levar nada de agasalho, não.
Não, eu só pus porque esse. Nossa, também tá horrível.
Hum?
Também tá horrível.
8 minutos.
Quantos minutos?
8, 7.
Acho que a gente vai. 10 pra gente ir lá em São Paulo, não.
É?
10 pra gente ir lá em São Paulo, não.
Ok. O Eduardo envia mais um. Ok. Correto. Cinco minutos. Carolina.
Pegar a luta.
Fiat Cronos. E aí, esse treinamento é bom ou não é?
Não é bom, mas é só que esse tipo de avaliação que eu não queria fazer.
Ah, não.
Uhum.
Não foi.
Eu não queria fazer.
Ah, ok. Tudo que a gente falou.
Tá bom? Beijo, tchau.
No, 1 minuto.
tá com o cabelo lá em São Paulo. Meu cabelo tá tão feio. Ouviu, meu bem?
Não, não vi nada, não. Falou.
Você deve arrumar meu cabelo lá em São Paulo. Meu cabelo tá tão feio. Eu não acho ninguém que arrume meu cabelo direito.
Ah, eu não vi, velho. Mês passado, 2 noites, eu coloquei lá na vizinhança para ver se eles querem fazer melhor, não. Oi. Não entendi.
Vou fazer minha comida tá toda aqui.
Hã?
É. Não aguentei comer.
Oi.
Que você toma da Ozempic?
Meio.
Meio mais.
Só meio. Por que você tá perguntando?
Não, aqui o meu, eu contei 60 cliques.
Ah, você quer saber quantos cliques?
É.
Ah, tá escrito lá, ué, preciso ver. Eu não recordo disso, não.
Deixa eu
Tá
ver.
escrito lá.
Vou ver se.
Bem, eu agora só estou inserindo 5 contos no arquivo final e já vou colocar ele lá no Drive e te mandar o link, tá? Consegui aqui dar uma estruturada no todo. O que eu vou fazer agora estou digitalizando aqui 5 contos que eu estou achando mais interessante e vou colocar lá. Então, só isso, eu já mando para vocês o link do material todo.
75 é 1 miligrama. Metade de 75 é meio miligrama, e assim por diante. Ah, olha só, o que ela respondeu, ó. Os rendimentos dos recursos de subvenção podem ser utilizados na execução do projeto, mas para isso é preciso antes ser autorizado pela FINEP. Você precisará encaminhar um ofício solicitando autorização e justificando a utilização desses recursos. Com essa autorização, é de competência da área operacional, creio que o ABIB. Ah, tá. Como essa autorização é de competência da área operacional, creio que. Ah, ok, agora eu entendi. Eu não tinha entendido antes. Oi,
Oi, tô
tá
aqui.
olhando aqui?
Uhum.
Tá, então precisa autorização e justificando a utilização desses recursos. Como essa autorização é de competência da área operacional, creio que a dona Bíblia, analista, poderá lhe orientar melhor nesse sentido. Quando os rendimentos dos recursos e contrapartida para extratar recursos próprios da empresa, não é necessária autorização pelo FINEP para a utilização do projeto.
É
Ok.
porque o dinheiro é de você.
Uhum. Ok, a questão é do. Mas o problema é que o rendimento vai variar, né? Porque o rendimento fica sendo ajustado à medida que o tempo vai passando. Tá bom, então já foi. Ok, então já foi esclarecido. A questão é só fazer um ofício, né?
Uhum.
Justificando a utilização desse. Ao solicitar a autorização e justificando a utilização desses recursos. É isso que precisa ser feito. Ok. Então a gente tem que fazer uma. Olá, César. Oi, o que foi?
Tem que conhecer o mingau para você.
Mingau? Mingau. Agora vai demorar para amadurecer os outros. Vai. Foi, o que foi? Oi, o que foi?
Não, tô rindo do Davi.
Hã?
Tô rindo do Davi.
Por quê?
Não, porque toda hora ele manda uma mensagem.
Tá muito alto esse barulho, meu amor? E se a gente for lá no quarto, será que fica incomodando ainda?
Por que que voltou o barulho alto?
Não, porque eu tô ligando ele. Eu liguei o negócio, o compressor faz esse barulho mesmo. Eu não tava ligando ele.
Olha, tá? Eu fui lá no quarto, dá pra gente ouvir daqui.
Mas tá incomodando ou não? Uma coisa é eu dar pra ouvir, outra
Sim,
coisa.
vai dormir. Pra dormir incomoda.
Oi,
Porque a gente for dormir, a gente desce.
oi. Tá vendo? Tá comendo?
Então, sim,
Né?
eu costumo tomar banho.
Né?
Mas é de leite, você tomar, você vai ficar no banheiro.
Que?
Não tem problema. É farinha láctea.
Não posso tomar do copo, não?
Pode, mas tá quente.
Ah, tá. Então espera esfriar. Espera esfriar. Já esfriou?
Não, prova.
Por quê?
Eu não tô usando.
Não, tudo bem, você tem que falar a sua também, né? Eu não quero provar do colher porque era muito pouco. Pouco açúcar?
Não, não posso. Bom,
Posso tomar tudo?
bom.
Pode ir. Farinha láctea.
É.
Check out. This for A and for B. Mais isso. Você colocou leite ou você colocou água com a farinha láctea?
Leite e água.
É. Misturou o leite com a água?
E a farinha.
Aham.
Porque se não colocasse a água.
Não, não, não. É que eu não posso tomar leite, lembra?
É, porque tinha leite aí.
É. 0.7. Line 61. Oi. Oi. Oi? É, pois é, pessoal. É.